Hello, my dear student friends. Welcome back to our channel. So, before watching this channel, please subscribe and press the bell button. Okay. So today we are going to discuss on root locus technique. Okay, root locus technique. What is the root locus? This is a technique used to determine the gain and the path of the roots. Okay. So the root locus plot gives a performance, system's performance for any value of system gain, right? So consider a second order closed loop transfer function characteristics. So today's topic is a root locus diagram. Okay, root locus diagram. Consider a closed loop transfer function, second order transfer function CFS by R of S equal to k omega n square divided by s square plus 2 zeta omega ns plus omega n square. This all of us know, right? We know this characteristic equation. So the characteristic equation, in the characteristic equation, sorry, this is a closed loop transfer function. The characteristic equation is the denominator of the closed loop transfer function, that is s square plus 2 zeta omega ns, okay, plus omega n square equal to 0. So this characteristic equation is changing its coefficients, will change the roots, okay, thus giving a different type of performance. Clear? So the roots of the characteristic equation are the poles of closed loop transfer function, right? The roots of the characteristic equation. This roots of the characteristic equation are the poles of closed loop transfer function are called poles, because denominator roots are called poles, numerator roots are called zeros. So poles of the closed loop transfer function. Okay. Therefore, changing the gain will change the values of poles, closed loop poles of the transfer function. Adjusting the gain value k, improves to improve the system performance. Adjusting the gain can improve the system performance without changing the gain, right? So therefore, changing gain will change the values of poles of a transfer function. Adjusting the gain will improve the system performance without changing the amplifier gain, right? So what is a root locus plot? Consider a closed loop transfer function in the system. Say consider the closed loop transfer function, the system, say R of S. This is the G of S. G of S, the forward transfer function. Then this is the feedback, H of S, feedback element. Okay. So C of S, R of S. Clear? So what is the roots of what is the root locus plot? So the root locus plot will give a system performance at any value of the gain, So here we consider negative feedback closed loop system whose the closed loop transfer function T of S, closed loop transfer function T of S equal to G of S divided by 1 plus G of S. This we know as usual, right? So the denominator of closed loop transfer function is called characteristic equation. 1 plus G of S, H of S equal to 0. So this is called a characteristic equation. Understand? Characteristic equation. Here, the modulus of this characteristic equation, which satisfies that the characteristic equation satisfies satisfies, okay, satisfies when the modulus of g of s, h of s equal to 1, and the angle of g of s, h of s should be equal to 180 degree. 180 degree. So the process of finding the points on the S plane which satisfy the above this condition, okay, conditions is the basics for root locus method or root loci, right? Root loci. So is a graphical method to find the position of roots of the characteristic equation or the poles of closed loop transfer function. Let us see in brief about this. So what is meant by a root locus diagram? Okay, root locus diagram is the graphical method. Okay, RLD root locus diagram is the graphical method of analyzing and designing a system. Method for analyzing, graphical method of analyzing and designing a system. Okay, designing a control system. Designing a control system. Okay, understand? Control system. So the root locus plot of the root locus diagram is a plot of loci of roots, locus of roots, root, okay, of the characteristic equation, while k is the varying from 0 to infinity. So actually the loci, the root locus plot varying from k equal to 0 to infinity, okay, 0 to infinity. If the gain is varied from k from minus infinity to plus 0, the diagram is called inverse or complementary RLD diagram. Suppose when this is when the root loci varying from 0 to k, varying from 0 to infinity, this is called root locus diagram. When k is varying from minus infinity to 0, this is called inverse RLD, or complementary RLD, or complementary RLD. Understand? RLD. If more than one parameter is varied, the corresponding diagram is called a root locus diagram. Okay, if more than one parameter is varied, okay, the corresponding diagram is called root locus diagram. Clear? Say let us take a system. Say when say here when k varying from 0 to infinity, root locus diagram. When k varying from minus infinity to 0, minus infinity to 0, or 0 to minus infinity, or 0 to minus infinity, this is called complementary diagram, complementary or inverse root locus diagram. When k varying from minus infinity to plus infinity, then this is called complete RLD. So this is called complete RLD. So this together for inverse RLD or this, right? So when multiple parameter varies, when multiple parameter varies varies, This is called root contour. Okay, root contour. This is called root contour. So this is where this k is nothing but gain of the system. That you know that, right? Say when the characteristic equation, in the characteristic equation, g of s, h of s, the characteristic equation, okay, 1 plus g h of equal to 0, then let g of s, h of s equal to k into g1 h1. Okay, let us assume. Similarly, when g h equal to k into g1 h1 of s equal to -1. So when this -1, the magnitude, already I mentioned the magnitude, understand, magnitude of g of s, h of s, magnitude of g of s, h of s equal to 1, right? So this is equal to 1. That is g of s, h of s modulus, okay, magnitude, this equal to 1 or k into g of s, sorry, g1 of s, h1 of s, h1 of s equal to 1 or k equal to 1 by modulus of g1 of s, h1 of s, h1 of s, or modulus of g1 of s, h1 of s equal to 1 by k, equal to 1 by k. Understand? So what about the phase of the g of s? The phase of the g of s, the phase angle, phase of g of s, h of s, gh, right? Phase of g of s, h of s. So the angle of gh equal to plus or minus 2 say epsilon plus 1 into pi, okay, where epsilon equal to 0, 1, 2, etc. Okay, so epsilon equal to 0, 1, 2, 3, etc. Any point in the S-plane which satisfies this here, any point in the S-plane which satisfies the above equation, above magnitude as well as the phase angle condition will lie on the root locus diagram of the system. Understand or not? Any point on the S-plane, okay, any point on S-plane, okay, which satisfies the above condition, the magnitude, this magnitude condition, and this phase angle condition, then then it will lie, okay. So the condition will lie on the root locus diagram of the system, okay, which satisfies. Understand or not? So which is a RLD, understand, my dears? See, let's see one simple example. Before discussing this, let us first see the poles and zeros. Okay, so normally poles and zeros of the system. This is the S-plane. We already discussed in S-plane. So this is S-plane, where this x-axis is the real, y-axis is the imaginary axis. Okay, so minus j omega plus minus sigma. So this is called origin 0. Okay, so we are going to indicate hereafter. We are going to indicate the int mark or poles. So this are all poles. The circle with the point. So this symbol represent 0. Okay, 0. So poles int mark 0. Round circle point is 0, right? So let us see what are the rules to construct a root locus diagram. What are the various rules? Okay, rules to construct root locus diagram. Rules to construct. First rule. So what is the first rule? Every branch of each branch of RLD starts at a pole. Okay, each and every branch, each and every branch of the RLD starts at pole, at poles. Okay, start poles. When it starts, k value equal to 0. When it starts, when k equal to 0. When it ends, k equal to infinity. Okay, when it terminates, at that time the gain value become infinity. Right. So each pole of each branch of the root locus diagram starts at poles with the gain k equal to 0 and vanishes or terminates at a 0. Okay, at poles, each pole start at a pole, terminate at a 0 or 0 when the time in is 0 at the time when it terminates k equal to infinity for root locus diagram of at a 0 of the open loop transfer function of g of s h of s. So g of s h of s. So each branch of the root locus diagram starts at a pole and terminates at a 0, right? Next point is the number of branches. The number of branches equal to number of poles. So the number of branches equal to number of poles. Okay. So number of branches of RLD root locus diagram equal to number of poles. So what is the condition? So let n number of poles. Say n is number of branches. This is equal to poles. If P greater than or equal to Z. Z is 0. This is equal to Z if Z greater than or equal to poles. Right. So this is called order of the system. So nth order of the system, where P and Z are poles and zeros of the number of finite poles and zeros of GHS. So number of finite poles and GHS. Understand? So the number of branches equal to number of poles. Another condition. So suppose let us take one example. G of s, h of s equal to say s plus 1 divided by s plus 2, s plus 3. So in this couple of transfer function, the poles are s at -2, -3. So zeros are z equal to sp poles s0, s is equal to 0 at -1. So how many poles are here? Only 2 poles. So there will be 2 branches. Okay, there will be 2 branches. Understand or not? So totally the RLD of this system, RLD for this system, number of poles equal to 2. So there will be number of branches equal to 2. Among the 2, I also mentioned here, you see each branch of the root locus diagram starts, okay, starts at pole. Okay, so there are 2 branches actually. There are 2 branches since 2 poles. So so one branch, say, let us see in the diagram. So first let us mark the poles and zeros. So 0 at -1. So -1. So 1 pole at -2. Okay. 1 pole at -3. Understand? So now the condition is, so there are 2 branches in the root locus diagram. This is S plane. Okay. So number of roots in the diagram. Understand? So one pole, see here, the root locus always starts, the branch starts at poles. So the poles, it terminates at poles, ends at zeros. There are 2 branches. One pole can terminate at 0. What about the another pole? So another pole terminates at infinity, k equal to infinity, somewhere far away. Say one more rule is there. So where are the branches are lying here? So the branches are lying here. Okay, the branches, you see, you take first pole or 0. First pole or 0. You stand here. Okay, stand here. So stand here. From this point. So here in this point, you see the right side of how many poles and zeros? Right side of the 0. So at this point, from the 0 value, so you stay here. You see, you look into right side. So how many number of poles and zeros? So there are no poles and zeros. Okay, then move between this point, this 0 and pole. Okay, so move here. Now look back to right half of the S plane, right side of this pole. So you just look into this side. So now if you look into this side, you count how many poles and zeros, total poles and zeros to the right side of this point, this position, only 1 0, right? Then there between this 0 and the pole, there will be a branch. There will be a branch. Understand? So obviously, then you move from this point to this point. So you stay here, just stay here, stand here, just to look right side of the real axis. So how many number of total poles and zeros? So total poles and zeros are 2. So if the right side of the number of poles and zeros nil, then there is no branch. Also, if the right side of the poles and the right side of your position, the total number of poles and zeros, including poles and zeros, are odd, then there will be a branch. If the total number of poles and zeros are even, no branch lie between the poles and zeros, right? So from this point, right side, no, the total number of poles and zeros are even number 2. So even, okay. So there is no branch between -2 and -3. Now you go and stand here. Understand? Stand here. You just look back to this side. Count the total number of poles and zeros on the real axis. So now 3, 2 poles, 1 0. So 3. So 3 is even number. So in this area, there will be a branch. Understand or not? This is the simple concept. Okay, concept of locating the branches. Now, as I mentioned in the first point, each branch of the root locus diagram starts at a pole, terminate at 0, right? So see here, between this pole and 0, there is a branch. So let me take in another color. You see, so one branch out of two branches, one branch starts from here and terminate at this point. Terminate at this point. So this branch starts from here and terminates at this point. So this is one branch. You go here. So one pole terminate at 1, 0. So this branch terminate at 1, 0. The direction should be this side. So between this point, okay, so this point, from one branch starts from this pole and terminate at infinity. We don't know where it terminates. It's going. So when it starts here, k equal to 0. So here also it starts k equal to 0. Whereas this point when k equal to infinity. Understand? So this is the method of locating the root locus RLD branches. Understand? So the another point number 3 is the RLD is symmetrical with respect to the real axis. The RLD, root locus diagram, is symmetrical about real axis. Okay, real axis, right? Symmetrical about real axis. If the pole 0 plot is symmetrical with respect to any point on the real axis, right? If the pole 0 plot is symmetrical with respect to symmetrical with respect to any point on the real axis, then RLD is also symmetrical with respect to that point. Then RLD is also symmetrical about the point. Okay, about the point. Clear? Provided that the point does not have any poles or zeros. Provided that the point does not have any poles or zeros. Understand or not? So this is the another rule, right? Next, there is a term called, in the RLD diagram, there is a term called centroid. Okay, in RLD, okay, the term called centroid, right? Say centroid. Any C, sigma, C, anything can be represented. Okay, so what is centroid? Centroid is the intersection of the asymptote. What is asymptote? Asymptote acts as a guideline. So guideline, the axis of the guideline. Hello. Yes, sir. Sir, online letter, sir. Sorry. So the centroid is the intersection of two asymptotes. Okay, always lie on the real axis. So it is the point where the asymptotes. Okay, the asymptote also symmetrical, right? Asymptote also symmetrical. The centroid point should be real. You should not consider the imaginary. So there won't be any imaginary point in the centroid, right? So centroid is the intersection of any two asymptotes, right? Intersection of asymptotes. So intersection of asymptotes. So when the pole always originate, the branch originate from pole ends at 0. Understand? Pole originate at branch of the RLD always originates at a pole and end at either 0 or at infinity in the space. So when it terminates rather than the 0, other than the 0 point, so it moves towards infinity, gain at infinity. Say assume somewhere it is going, like gain is infinity. Suppose, so this point, okay. So this point, say there are 2 points. So suppose one pole here, another pole here. Another pole here. Say 1 0 is here. 1 0 is here. 0. So the here no branch. So between here, if you stand here, your right side odd number. So between these two poles, there will be a branch. As per the definition, as per the rule, the one branch of the root loci starts from this pole. Another root locus, branch of the root locus starts from here. They meet together and take a diversion. This is a breakaway point. Take a diversion. So when at what angle it take diversion? That is with the guidelines of centroid point. Understand? So that is called asymptotes. So these two are asymptotes. The meeting point of the asymptote is centroid. The meeting point of two asymptotes. What is asymptote? What are asymptotes? The asymptotes are guidelines to the branch of RLD which terminates at k equal to infinity. Understand or not? So that is the condition, right? So this always, the centroid is always lie on the real. Okay, centroid is always real. Okay, always real value, not imaginary, real value. So the number of asymptotes, as I say, the modulus of number of poles and number of zeros should be equal to a number of asymptotes. Say in this case, you see, in this case, let's see. Say in this case, you see, say how many poles? 2 poles. Say poles is 2. How many 0? 1 0. So 2 minus 1, how much? So number of poles minus 0, 1. So how many asymptotes are there? So this is equal to 1. 2 minus 1, 1. What is the asymptote value here? Which is the asymptote? So this line is asymptote. So the second branch terminate at k equal to infinity. K equal to infinity somewhere. So it travels along the real axis. Can you tell me what is the angle of this asymptote? The angle of this asymptote, the angle of the asymptote is 180 degree, right? So from this reference line, the angle of asymptote is 180 degree. So the asymptote guide the root loci, okay, to the from poles to zeros, right? So which lie at infinite. So which lies at infinite, right? So see, what is the angle of poles, right? Sum of how many centroid, how to calculate centroid point. So the centroid equal to sum of real part of poles, sum of real part of poles, minus sum of real part of zeros, right? Divided by pole minus 0. This is the centroid point. So how many, say in the previous case, how many real poles? This is the centroid meeting point of the asymptotes, right? So how many poles here? So 2 poles. So real part of poles. So real part of pole number. Okay. So what is the real part of pole number? So 3, right? Sum of real part of pole numbers. So 2 plus 3 equal to 5. 5 minus, real part of poles, 2 plus 3 plus 2, 5. 5 minus 5, this 3, real part is 3, then 3. So sum of real part of pole, the zeros of GHS, 3 plus 2, 5. 5 minus 1, 4, divided by P minus is that, so 1. So 4. So where is that guideline? It is towards the pole. So angle of asymptote is centroid point at the 0. So actually here there is no multiple poles here, right? Sum of real part of poles minus sum of real part of zeros of G of H of S divided by P minus Z. So then next is angle of asymptotes. Okay. 1, 2, 3, 4, 5. Right? Angle of asymptote. So angle of asymptotes. So angle of asymptotes. So what is angle of asymptotes? Theta A, say consider angle of asymptote is theta A. Angle of arrival departure is there. So asymptotes, say AT, theta AT, asymptotes, right? So this is nothing but theta asymptotes equal to 2n or 2m plus 1 into pi divided by P minus Z, where m equal to 0, 1, 2, 3, etc. up to P minus, we have to put it the value up to P minus modulus of P minus Z minus 1 up to the total number of poles minus 0 minus 1. So up to this, we have to substitute m value first 0, 1, 2, 3, etc. Right? So next is on the real axis to the that section I explained, right? Where the RLD branches of RLD exist. Okay. Then how to determine the value of K? Determination of value of K on the RLD, okay, at any pole at S equal to S1 at any point on the root locus diagram, we can calculate the K value. So what is the K value formula? So K value equal to, so K equal to K at any point S equal to S1, which is equal to product of distance, product of distance vectors from various poles poles of G of S, H of S to S equal to where we want to get the gain value, right? Where S equal to S1 whole thing divided by same product of distance vectors from various zeros of G of GH, okay, G of S, H of S to S equal to S1. Understand? So this is where S1 is the point on the RLD, or from the magnitude condition. Okay, we can also calculate from the magnitude condition. K can be calculated. How to calculate the magnitude condition? So we can calculate. So S1 is the point, is a point on the RLD, root locus diagram, point on root locus diagram, RLD. Or we can also calculate, so from the magnitude expression, also we can calculate K. So what is K? K at S equal to S1 is nothing but, we already calculated very beginning, modulus of G1 of S and H1 of S at S equal to S1. From this condition also, we can able to calculate the gain value, K. Okay. Next is break away and break in point. Break in or away. Okay, points, or this also called saddle points. Okay, so break away or break in points. So where the break in and break away points exist, okay, when two poles meet together, say from this say S plane. So in the S plane, suppose here one pole, here one pole is there, right? Understand or not? So how many branches are there? Since P equal to 2, branches also 2. So one branch starts from this pole, say P1, this is P2. One branch starts from here, another branch starts from here, P2. One from P1, one from P2. Where to terminate two branches? They terminate at infinity because there is no zeros in this system, right? So when they meet together, say like two villains or two heroes meet together, fight together, then they will break away, they move away. So this branch P1 pole branch terminates this side, P2 branch terminates this side. Okay, so when they meet together and take away, so that is that point. The point is called This point is called break away points. Okay, so when break in or away points exist when there are multiple routes. Either this is a break away. Okay, where the break in points occur, right? Suppose say here 1 0, here 1 0. Understand? Suppose Okay. Say here somewhere here a complex pole is there, one complex pole. So another complex pole somewhere here. So there are two poles. So two poles, either complex or real, that is immaterial. There are two poles. So two branches are there. So one. Say this is P1, this is P2. Okay. So one pole starts from here and end at 0. Okay, two zeros are there. So when two zeros are there, one branch comes here and enter into a point. This is called break-in point. So this branch moves from here and meet this branch, right? So this meeting point is called break-in points, right? So breakaway or break-in points exist when there are multiple routes on the root locus diagram. En route achieve, arrive or depart at the break-in points. Okay, en route of loci arrive or depart at the breakaway point by an angle of 180 degree and apart. Okay, 180 degree by n apart. Understand? So en route loci arrive at the break-in point by the angle of 360 degree by n apart. Okay, so en route, say en route loci arrive or depart at the arrive at the break-in or away point by an angle of 180 degree by n. Similarly, en route of the loci arrive at the break-in point by 360 degree. Okay, break-in point by 360 degree by n. If en route loci depart at the break away point by an angle of 360 degree, whether arrive or depart by 360 degree, whereas en route loci arrive or depart, both arrive or depart in breakaway or break-in point, so they are called, the break-in or breakaway point is 180 degree. The en route loci arrive at the break-in point by the angle of 360 by n apart. En route loci depart at the break away point by an angle of also 360 degree by n. Okay, if the break in or away point, break in or away points, K is breakaway point or break-in point. The K is, okay, breakaway. Both, if the both at the break-in point or away point, the value of K, okay, when break at the break away or break-in points, K is either maximum or minimum. Okay, K is maximum or minimum. Understand? Maximum or minimum. So how to determine the gain value K? Okay, so that this can be determined from dk by differential of K by with respect to s and equal to 0 will give the roots roots are break away or in points. Break away or in points. Break away or in points. Dk, okay, dk by ds equal to d by ds of 1 by the g1 s h1 of s. Okay, so which is equal to d by ds of, okay, d by ds of g1 h1 of s equal to 0. Okay, d1 h1 equal to 0. So this equation is a necessary equation. At the valid breakaway point, at the valid break away or break in, break away at a valid break point, break away or break in point, angle of g of s h of s equal is odd multiples of plus or minus 180 degree, odd multiples of 180 degree. Understand? So how to determine the roots of breakaway or break-in point? By differentiating the k value. Okay, k value on the closed loop transfer function. So then angle of departure. So then angle of departure. Angle of departure theta d. Sorry, theta d. Then angle of arrival, that is theta a. Assume theta a. Okay. So angle of departure or angle of arrival at a 0 of at a, so where it arrives, so the angle of departure from the pole, okay, so from the pole it departs. So similarly to the 0, okay, to the angle of arrival to the 0 or to the 0 or at the 0 to the 0. So arrival, so from the branch originate from a pole and arrives to 0, right? So angle of arrives 0 in the RLD, right? So what is the formula? So theta a theta angle of arrival equal to 180 degree plus 5 or 180 degree is equal to theta a equal to 180 degree minus angle of GH at S equal to S1, at S equal to S1. Understand? At S equal to S1. So what is angle of departure? 180 minus 5, okay, or otherwise 180 plus angle of GH at S equal to S1, where 5 equal to, okay, angle of poles minus sum of angle of zeros of G of S, H of S at S equal to S1. Understand or not? So these formulas are very important. Please remember, for angle of departure, this is plus, here minus. Okay. Similarly, angle of arrival, here minus, here plus. Understand or not? So this concept also very important. Next is point of intersection of RLD with respect to imaginary axis. So point of intersection, okay, POI, point of intersection of RLD with respect to imaginary axis. So how to determine point of intersection of the RLD with respect to imaginary axis? This can be calculated from the Routh-Hurwitz criterion, right? So we know the open loop transfer function. So make it to characteristic equation 1 plus GH. So from the 1 plus GH, we can find K, okay, by equating rows, the K by equating rows of S equal to 0, and use the K in the auxiliary equation. So when the rows of previous row, right, that is rows of S square in the RH table, then auxiliary roots of R point of intersection, that is plus or minus j omega. Okay, so this can be calculated. This can be calculated from Routh-Hurwitz criterion by Routh-Hurwitz criterion, right? So determine K by equating row of S, okay, row of 0, okay, and use this K, and use this K in auxiliary equation. You know auxiliary equation, we already see, right? In auxiliary equation, that is row of, so this is a row of Z or S, right? Row of 0 in S row, right? This is row of S square, okay, S square in RH table, understand? So the auxiliary equation or point of intersection in the imaginary axis, that is plus or minus j omega n, plus or minus j omega n. Understand or not? Okay, these are all the rules. So please go back. See, first rule, first keep in your mind, each branch starts, okay, each branch of the root loci starts at a pole and terminate at 0. If sufficient zeros are not there, the branches terminate at k equal to infinity. Okay, whenever the branch starts, k value is the k gain value is 0. Whenever it terminates, either at 0 or at wherever far away point, we don't know the exact location. So at that time, the gain value equal to infinity, right? Understand? So let's see one example, then you can easily understand. Clear? See, sketch the root locus of a system having loop transfer function GH of S equal to K into S plus 5, and also determine the range of K for stability, right? So the GH is given. What is GH? K into S plus 5 divided by S square plus 4s plus 20. Understand? So this is KH, right? So what is the poles? What are the poles and zeros? Understand or not? So solution. First, find the poles and zeros, right? So what is this minus b? Here are two poles. Two poles are here. So what are the two poles? So minus b minus 4 plus or minus square root of 16 minus b square minus 4ac. 4ac 20 divided by 2a 2. So yes, p1 p2 poles. So minus 4 plus or minus square root of 16 minus 80 divided by 2. So what is 16 minus 80? Please tell me. 16 minus 80. So 64, right? 64. Square root of 64 is 8. Minus 4. 60. B square minus 4ac. 4ac. 4ac, right? Branches are minus, okay? Minus 64. Square root of 64, 8. So P1 and P2. Say simply, you can, this is inside, this is minus 64. So I square 8, J8 square. So 64, so 4. So we will be getting minus 2 plus or minus J4. Okay. So two poles. So two poles are there. So poles are at minus 2 plus J4 and minus 2 minus J4. So 0 at, first calculate poles and zeros at S equal to minus 5. So number of poles Pn, number of poles equal to 2, number of poles equal to 2, number of zeros equal to 1. So can you tell me, my dear student friends, what is the number of branches of the root loci? How many branches are there in the root loci? Anybody? Any idea? Any idea? So the number of branches in the RLD is 2. So since the number of poles equal to 2, so number of branches in the system is also 2. Okay, so number of poles equal to 2, number of zeros equal to 2. So the number of separate RLD branches equal to 2. So 2 branches. Okay. Since it has 2 branches, you can easily tell the order is second order, right? The order is second order. So our system is second order. So number of asymptotes. Next, number of asymptotes, okay, equal to P minus Z. So 2 minus 1, 1. Say how many zeros are there? How many poles are there? So 2 branches. So one branch will terminate at 0. Okay. So one branch of RLD terminates. Okay. Terminates at a finite zero. 0 value we know, that is -5, right? 0 at s equal to -5. Okay, because p minus z is 1. Hence, the second branch, okay, one branch terminate at finite 0. The another branch, okay, another branch will terminate at infinity, okay, at infinity, right? So what are the starting points of the branches? The two branches start from two poles, clear? So the starting point of the branches are at the two poles, P1 and P2. So pole 0 flat, okay, let us draw the pole 0 flat for this diagram. So the pole 0 flat, okay. So what is the pole 0 flat? So you see, so real imaginary axis minus j omega, okay, so minus sigma. So one pole at -2, real value is say 1 2, so -2 plus j4, okay, plus j4 minus j4. So one pole here, right? Another pole here. Understand? So we mark the pole into mark. So one pole here, another pole here. So next 0 is 5 at the 5, -5. So we draw in this fashion, -5. Okay. So see, from the, what is the next step after drawing the pole 0 plot? So see, where are the two branches possible in the RLD, the pole 0 plot? What are the two possible branches? So see, you stay here, okay? So -2 here, you stay here. Just look to the right side. So how many poles and zeros, total poles and zeros? How many total poles and zeros? Nothing. So no branch in this real axis. So in the axis. Then stay here. Understand? Stay here. You come and stay here. Stand here, look back. How many number of poles and zeros? So how many number of poles and zeros? So there are two poles, one pole here, another pole here. So two poles. So 2 is the even number. Okay, 2 is the even number. So here also no branch between this and this. Okay. Now you go here. Now look back this side. Just see. So how many number of poles and zeros? So 2 poles, 1 0, totally 3. So odd number. So definitely the branch will be available here. Definitely branch will be available here. Understand? Understand or not? So there is no branch here and here. So branch is not available here. So only branch is available in this area. So actually this is a 0. So from among these two, say among this pole and this pole, among these two poles. So one pole, okay, any one of pole will terminate at this point. So the direction should be towards this, because some branch from among these two poles, one branch will reach this 0, right? One branch will reach this 0. So there it is coming far away from them, right? Let us find the uh, uh, angle of asymptotes. Okay, let us find the angle of asymptotes for this. So this point, first we fix this. This is plus J4. This is minus J4. So let's find angle of asymptotes. Angle of asymptotes. So what is the formula for angle of asymptotes? Theta at equal to 2m plus 1 into 180 degree divided by p minus z, where actually how many poles minus 0? Only 1. So m value starts from 0 to p minus z minus 1. So p minus z is 1, 1 minus 1 is 0. So only one term we can calculate. So this equal to 2 into 0 plus 1 divided by 1 into 180 degree. Okay. So what is the value? So 180 degree is the angle of asymptotes. So the angle of asymptote is 180 degree. So the asymptote is moving in this direction. So 180 degree. Angle of asymptote is 180 degree. Understand? Next, let us calculate the centroid. So what is centroid? Meeting point of the asymptote is centroid. So where is the centroid point? It starts at the break-in, breakaway point, right? So let's calculate centroid. So what is centroid? Meeting point of the asymptotes. Centroid. Okay. As there is one branch approaching to infinity and only one asymptote exists. So the centroid is not exist, right? Centroid is not existed, right? So only one point. So since only one point is approaching to infinity, and see here also only one asymptote, right? Only one asymptote and only one asymptote exist. So there centroid is not exist. There is no centroid. Okay, understand or not? Okay, next is breakpoint. So what is breakpoint? Okay, so for that we have to differentiate. To get the breakpoint, you see back breakpoint. The break-in, breakaway saddle point. To determine saddle point, so dk by ds equal to 0. Clear? dk by ds equal to 0. So what is g1 of h1 of s? The g1 h1 of s equal to s plus 5 divided by s square plus 4s plus 20. So dk, differentiate this with respect to s. Okay, understand or not? So denominator square, s square plus 4s plus 20 the whole square. Understand, my dear student friends? Please do it. S square. Please tell me the answer. Let me wait. S plus 5 into differential of this. Okay, 2s plus 4. This should be equal to 0. So differentiate this becomes 0. So you will be getting this equal to 0. So s square minus 2s square minus 2s square, 2s square into 4s. Okay. So the answer minus 2s square minus 10s. Simply you can tell me the answer. Correct, correct. Tell me, correct. Your answer is correct. 10s, sorry, minus 4s minus 20 plus s square plus 4s plus 20 equal to 0. Okay, plus 20 equal to 0. So what we are getting? Simplifying, we will getting 110 s equal to 0. So taking s common, s plus 10 equal to 0. So s equal to 0 and s equal to minus 10. So s equal to minus 10. The s equal to 0 means, you see, there is no branch in this s equal to 0. So the s equal to 0 is not a valid breakpoint. So s equal to minus 10 is the breakpoint. S equal to 0 is not valid breakpoint. Okay, so s equal to minus 10 is a valid point. S equal to minus 10 is valid. Okay, so this point only lies on the RLD diagram. So you see, so where is minus 10? So minus 10 here. So this is breakpoint. So what is breakpoint? Minus 10. Breakpoint is minus 10. Next is intersection with the imaginary. Intersection point. Point of intersection. Okay, POI with the imaginary. Intersection point. Let us consider the characteristic equation. What is the characteristic equation? S square plus 4s plus 20 plus k. 20 plus k into s plus 5. K into s plus 5 equal to 0. Understand? The numerator party will be coming here. So the s square plus 4 plus k s 4 plus k s plus 20 plus 5k. But students, understand or not? So let us form the Routh array for this. So the RHT, the Routh array table, Routh Hurwitz table is s square s1. Okay, so 120 plus 5k. Here k plus 4, 0. So here k plus 4 into this minus 0. So this will be 0. Divided by this 20 plus 5k will be coming here. Okay. So what is k max? So k max is minus 4. K max is minus 4. Makes the row of 0. So this say, if you want to make row of 0, k should be equal to minus 4, right? K should be equal to minus 4. But as it is negative, there is no intersection of root locus with the imaginary, right? So since k is negative, there is no POI on imaginary axis. Understand? So next, next is angle of departure. Angle of departure. So angle of departure, theta d. So what is the formula for angle of departure? Okay. So for that we have to determine the vector length. Vector length, right? So again we go back to the pole zero diagram. S plane. S plane. Okay. So here is 2. Here is 4. Here is 4. So plus J4 minus J4. This is minus 2. Here is 5. Minus 5. Okay, this one pole. This is another pole. So 2 poles are there. Okay, let us calculate the pole angle. Okay, made by P1 to P1, angle of P1. Clear? So what is the P1 angle, theta P1? See, say this is P1. Say this is P2. So from this to the another pole. Okay, other pole. So what is the angle made by this pole with respect to this? So 90 degree. So theta P1 equal to 90 degree. Similarly, what is the zero make with this point? So this point. Okay. So this angle is theta PZ. Sorry, theta Z. Z1. Theta. Sorry. Theta Z1. Theta Z1. Theta Z. Only one is Z, right? Theta Z. So how to find, say, this magnitude, calculate this magnitude is 4. This magnitude is 5 minus 2, 3. So tan theta equal to opposite by adjacent, right? Tan theta is opposite by adjacent. So theta Z equal to tan inverse of 4 by 3. So what is tan inverse of 4 by 3? Please calculate and tell me, dear students. Tan inverse of 4 by 3. Okay. 4 divided by 3. Okay, right. 53.113 degrees. Theta Z equal to 53.13 degrees. 53, right? So what is phi? Phi equal to sum of delta angle contributed by the poles minus sum of contributed by zeros. Okay. So what is the value? Please tell me. 90 minus this 36.88. So sorry, 90 minus 53. So 90 minus 53 is around 36.9. Okay, 36.9 degree. So that is the phase angle. So what is the formula for angle of departure? Angle of departure equal to 180 minus 5. So that is equal to 180 minus 36.9 degrees. So please tell me the angle of departure value, my dear student friends. Okay. So minus, so at this pole, this is calculated angle of departure for one pole, right? So one pole, so this pole, right? So similarly, what is the angle of departure for this pole? So that is the negative version, right? So the angle of departure for with respect to P1 equal to 143.1 degrees Celsius. So this is for the pole of -2 minus plus j, sorry, plus j4. So then similarly angle of departure equal to minus 143.1 degree for plus 2, sorry, minus 2 minus j4 pole, this pole. This is for this pole. Understand? This is angle of departure. Next is finally from all the information we can able to draw the diagram. Okay, so here P1, say this is P1 or P2, P2, this is P1. Here say 0, this is the real axis, this is imaginary axis. So this value is plus J4. Clear? So this is minus J4. Okay. So this is minus 2. This is minus 5. So this direction. So this is the break point. So this is called break point. Break, that is break in point. Break in point. So what is break in point? Minus 10. Break in point. So one pole starting originates from here, another pole branch originates from here. So this branch originate at k equal to 0. Here k equal to 0, and terminate at this one pole terminate at this 0. This 0, a finite 0 at k equal to infinity. Another pole terminates originates here P2, and this branch goes like this and terminates at k equal to infinity. The k, so k increases towards this direction. Okay, here k increases to this direction. Say this is branch 2, this is branch 1. So this is branch 1, this is branch 2. So one branch B1 terminates at minus 5, this 0, B2 terminates at k equal to infinity. So when it originates from this pole, so what is the angle of departure? Okay, so when we have a complex poles, there will be, so for complex poles, okay, for complex poles, angle of departure. For complex zeros, we have to find angle of departure. Okay, theta d should find. Okay, find when complex poles are there. When complex zeros are there, we have to find angle of arrival. This is must. These two are must. So angle of departure, angle of arrival. So when it starts, when the branch starts from this point at k equal to 0, similarly at this point k equal to 0. So at what angle? So the angle of departure, at what angle the branch departs from the place, right? So that is the angle of 143. So say this is horizontal plane, so 90 degree vertical, say 143. So this angle is angle of departure. So this angle of departure is 143.1. Okay, so this is positive. For this pole, negative. Okay, negative. So this angle is minus 143.1 degree. So understand or not? So this is the S plane. This is the S plane. the root locus. This is the complete root locus diagram. Okay, let us see what are the k ranges of k for stability. Okay, for stable. Okay, stability. Understand? For stability. So what is the range of k? Stability is, understand? So for all ranges of k, that is from 0 less than k less than infinity, both roots, okay, both roots are always in the left half of the S plane. For the range of 0, k, infinity, from k 0 to infinity, range from 0 to infinity, all the roots are lie on the left half of the S plane. Okay, for all the roots are lie on the S plane. So hence, okay, all the roots, are always on LH plane. So system is stable. System is always stable. The stability, okay? Stability system is always stable. Understand or not? So the system is stable. Thank you very much, my dear students, friends. Please subscribe my channel and press the bell button. So your subscription will be shared with many educators and the students and the job seekers.